Look at this equation. Y squared equals x cubed plus 215. We want to find all integer solutions for x and y. It looks incredibly simple. It's tempting to start guessing small positive and negative numbers, but checking numbers one by one is not effective. Even graphing this curve provides no obvious integer coordinates. Our goal is to prove that absolutely zero integer solutions exist. To do that, we need to show that this equation contradicts itself mathematically. Let's analyze it step by step using modular arithmetic. First, we need to know if x is an even or odd integer. Let's check the behavior of the equation modulo 8. Let's assume x is an even number, so we can write it as 2k. Cubing 2k gives us 8k cubed. Because it's a perfect multiple of 8, x cubed is congruent to 0 modulo 8. Now we substitute this back into our equation modulo 8. We get y squared is congruent to 215 modulo 8. Since 215 is 8 times 26 plus 7, this simplifies to y squared is congruent to 7 modulo 8. But is it possible for any perfect square to leave a remainder of 7 when divided by 8? If y is even, its square modulo 8 is either 0 or 4. If y is odd, its square modulo 8 is always 1. A square can never be 7 modulo 8. This gives us a contradiction. Therefore, x cannot be even. X must be an odd integer. Now we know x is odd. Let's look at the equation again. We have x cubed on the right side. If we could rewrite the right side as a sum of cubes, we could factor it. Notice that 215 is exactly 1 less than 216, a perfect cube, 6 cubed. So let's add 1 to both sides of the equation. We get y squared plus 1 equals x cubed plus 6 cubed. Now we apply the sum of cubes formula. This factors the right side into x plus 6 multiplied by x squared minus 6x plus 36. Let's examine this quadratic factor. We will call it q. By completing the square, we can rewrite q as x minus 3 squared plus 27. Remember from our first step, x is an odd integer. This means x minus 3 is an even integer. When you square an even integer, it becomes a multiple of 4. So x minus 3 squared is 0 modulo 4. Evaluating q modulo 4, we get 0 plus 27. Since 27 leaves a remainder of 3 when divided by 4, q is congruent to 3 modulo 4. And because a square is always positive or 0, q must be at least 27, meaning q is a positive integer. Every positive integer is the product of its prime factors. If all of q's prime factors were 1 modulo 4, their product would also be 1 modulo 4. But q is 3 modulo 4. This mathematically guarantees that q must be divisible by at least one prime number p that is congruent to 3 modulo 4. Now let's apply this to the full equation. We know a prime number p divides q. Because q is a factor of the right side, p must also perfectly divide the left side. Therefore, y squared plus 1 is congruent to 0 modulo p, which means y squared is congruent to negative 1 modulo p. This tells us that negative 1 is a quadratic residue modulo p. But according to Euler's criterion, for any odd prime p, negative 1 is a quadratic residue if and only if p is congruent to 1 modulo 4. This results in a mathematical contradiction. We establish that p must be 3 modulo 4, but for this equation to have a solution, p must be congruent to 1 modulo 4. They cannot both be true. Because this contradiction exists, the original equation y squared equals x cubed plus 215 has no integer solutions. If you enjoy math explained with clarity and zero fluff, like this video and subscribe to Matilda Academy.